in my 4 to 2.
Recording in progress.
Want to start sharing your screen so we make sure you'll be able to show. Yes. Sharing your screen or not yet? No, through Zoom. I think you have to share also through Zoom. Yes. You can use the desktop and then go to the full screen mode. Okay. Good afternoon, everyone. So today it's a pleasure to have David Dardzinski from Adirondack Alternate Energy sharing some of his projects and talk about his experience working in the industry. So let's welcome David.
Thank you. Good afternoon. So I'd like to thank you, Professor, for inviting us. My business partner, Bruce Brownell, who you'll be hearing about, wasn't able to come today. He's been under the weather. So I'm going to give it a go by myself. We'll see how it goes. So I'm going to start by introducing myself, my experience in architecture and construction. I grew up in the suburbs of Philadelphia, Pennsylvania. I'm the son of an architect who happens to have studied architecture here at Syracuse when he was in the service and stationed in Rome at Griffith Air Force Base, but completed his degree in Philadelphia at Drexel University. And you might think, well, that's obvious, he would have his son follow in his footsteps, but that wasn't the case. He was always telling me to be a engineer or a lawyer because they make money. Architects, they do it for the love of creativity. So of course I figured I'd be a soccer player, a race car driver. However, I was one of 3 boys. I was the oldest. and we're very close in age. And so our family, friends, neighbors, strangers would refer to us as the devil's spawn. Even before we were teenagers, we were always getting in trouble. So since it was the 70s, we didn't have air conditioning. The summertime, our parents would let us sleep out back in a tent outside. Of course, that meant that we weren't sleeping, we were out, getting into mischief. One of the things we would do is we would go about half a mile to a convenience store, bodega type place, hide in the used car lot across the street, or more of a repair shop, and wait for the Amorosa bakery truck to arrive. If you're not from Philly, that's the best bakery in Philly. They do the cheesesteak hoagies. The rolls are great. Anyway, so we'd wait for the truck to come at like 4 a.m. and they would just drop off the buns and rolls and bread in these plastic bins, set them underneath the overhang and outside the door and leave. So we'd go over and we'd steal some rolls and eat. Well, one thing led to another, and we noticed that the shop left the windows open one night. And we're like, oh, we can climb in that window. So we climbed in, we got some keys, and took a couple cars for a drive. Now, not realizing at the time that, being 12 and 10, there's a reason these cars are in the shop. They're probably not safe to drive. But we did. We did that a few times over the summer till we got caught. Policemen saw us driving around, peering over the steering wheel. Of course, they, took us down to the station, booked us, photographs, fingerprints, took our belts, our shoelaces, put us in separate cells, took us separately, grilled us questions. It was all morning till they finally called our parents to come get us. Well, we got off because the guy that owned the shop didn't want to press charges, because then people would know that a 12-year-old, 10-year-old had stolen cars from his lot. So it was just basically fines, driving without a license, driving underage, driving without insurance, etc. As a consequence of that, I had to work the rest of the summer in my dad's architecture firm, running blueprints, taking the trash out, going to get donuts. He paid me $1 an hour, 50 cents towards my fines, and 50 cents towards my brother Michael's fines. So that's how I got into architecture. So it's been roughly, 50 years or so that I've been working in architecture construction. After that first summer, I started working for my dad in the summers until I got into high school. And then he kicked me out of the office. He said, go work in construction and learn to build what you're designing. If you really want to be an architect, you need to learn how to build things in real life, which was great because I learned a lot there. I learned that, a detail can be constructed different ways by different people. And as long as it's sound, there's no reason why the way I drew it on the drawing has to be the way it gets done in the field, especially if it's cheaper or easier for them to do it their own way. It actually helped too, because, things happen in life, and, I got laid off and ended up, working construction. And it wasn't my father who laid me off. So I did go to college, 4 universities, actually, one twice. But, financial, family, health issues derailed that. So I never completed that, which means that I didn't qualify to the intern development program, which is required to sit for the architecture exam. So I'm not an architect, though I've spent most of my life working in architects firms. I worked for 6 architects in New York City, Philadelphia, Baltimore, Phoenix. Actually, Phoenix, I worked for Nick Davini, who was an apprentice for Frank Lloyd Wright. So I've had a varied experience from, garages. I'll show you some pictures of my work, from converting a garage into a pool house to the Roosevelt Hotel in New York, or Flagstaff Medical Center Hospital in Arizona. I've also designed some buildings overseas, office building in a block manufacturing plant in Poland, warehouse facility in Nigeria, townhouses, condominiums, I guess, technically, in the Cayman Islands, some flats in Edinburgh, Scotland. And buildings that I've designed or worked on have won awards and competitions. So if you'll indulge me for a minute, we'll run through a couple of projects. This was a competition in Philadelphia, Archdiocese of Philadelphia, for a mausoleum complex and a chapel. Upper right is our presentation boards, and we also did a model, built a model of it. Obviously, we won and it got built. Clinical labs, the corporate offices were added to the lab building to the right there. This is a church outside Philadelphia. They spent 5 years raising money for this. They got to the point where they had enough to hire me, which isn't a lot. And I suggested that we build a model and put it out in the foyer. They're meeting, renting a gymnasium at a high school, and Sunday mornings they'd go in there, set everything up, and have their service. So we put the model out there and put a big bucket with the fund drive on it. A year and a half, they raised enough money to afford the financing to build it. So sometimes when you can see something tangible, even if it's just a model, it makes a big difference in people's perceptions, and they can understand and grasp it. It's going to happen. It can be something. This is it's an office building in Little Falls, New York. Car dealership. This is what it looked like before. Interesting story. There's my sketch there. After I originally designed the full building with those 2 bays at the back there, and the owner said, "Oh, I don't need those bays. Well, these 3 in here, first 3 are enough." Well, once it got built, his business took off, and a year later, we were building those other 2 bays because he didn't have enough space to service, wash, and clean cars. And I worked for some large corporations, Toll Brothers. I was a 200-unit, 300-acre development housing, and this was the original barn on the property. So we renovated that into a clubhouse. Some library in Northampton, Bucks County, Pennsylvania. And this is Sloatsburg service area on the thruway, just when you get out of New Jersey on 87. And well, there's the Roosevelt Hotel You may have seen that in movies. We did renovations to that in late 80s, early 90s. So it's, typical storefronts. It's an ambulance corps building. Houses. So this is the before picture. That's the approved sketch, the front elevation, and then obviously that's after. Apartment renovation. There was a fire there before and after. It's a duplex, well, two flats. Apartment on the first floor, apartment on the second floor with a roof deck. That's on the Erie Canal. That hasn't been built yet. And there's a couple of apartment buildings. I think it was 4 apartments on an empty lot in Lambertville, New Jersey, on Delaware River. This is a land bank project, Greater Montgomery Land Bank. It's a trailer park. It's one of the existing trailers. They got a grant to replace them with zero energy modular houses. So what we were able to do, the state helped with, and the land bank, we converted their heat money, or the money that they're spending on heat and electric, because the zero energy modulars have no bills for heating electric. Solar panels on the roof, some battery backup. So that became their mortgage payment. So instead of paying for heat, they're buying a house with that money. And that's under construction now. And this is just a house on a lake, Pleasant Lake in the Adirondacks. That's the vacant lot up there. That is the existing house next door. Sketch plan, the 3D model. So I present that to you because I've worked all over the country. I've worked outside the country. And I think, in my opinion, what Bruce Brownell has done with Adirondack Alternate Energy surpasses what I've done. Bruce is not sort of a local legend and a passive solar energy pioneer. Passionate about sustainable forms of energy, he has spent the last 60 years designing, constructing, and studying passive solar buildings, identifying the monetary and health benefits, and then sharing, educating students, clients, and general public. Bruce was born in Edinburgh, New York, which is inside the Adirondack Park on Great Sacandaga Lake. I don't know if you're familiar with that. It's north of Gloversville, Amsterdam. He was born to a lumberman whose grandfather was a lumberman. His grandfather had a mill on Sacandaga River before the reservoir was flooded, became a lake. His father started a lumber business, Brownell Lumber. Bruce worked there as a young kid. He also experienced construction firsthand because his father started building camps for vacationers coming up from downstate. 2-bedroom on stilts along the lake shore, off the lake. And so Bruce was involved in that from an early age. As a kid, I was outside all the time, he'll tell you. In winter, I noticed that on southerly slopes, under low-hanging limbs of pine trees, the ground was always bare of snow. I used to crawl in there, take off my jacket, and feel completely comfortable. This enduring childhood experience would lead him to explore ways to harness this energy from the sun and heat houses and other structures. After high school, he served in the Army before entering college. He earned his degree in construction management and wood products engineering from SUNY College of Environmental Science and Forestry. Whoop, whoop. He graduated in 1964, so he's a little before your time. He has a long list of accomplishments, too many to realistically list in the time we have, from engineer to advocate, educator to builder, employee to public servant. Bruce went from grading lumber in the Pacific Northwest to building and operating a go-kart track, owning a marina on the Great Saginaw Lake, as well as owning an airport. He also owned and operated a real estate company, planned and built housing developments, and of course, built over 400 passive solar houses with Adirondack Alternate Energy. By 1970, Bruce was so established as a passive solar energy voice in the US, he was invited to speak to the first Earth Day in Flushing Meadows, New York City World's Fair site, about passive solar design and its benefits. In 1981, Bruce testified to the US Congress on passive solar energy and its potential. So you might be wondering, did Bruce Brownell discover or invent passive solar heating? Well, as much as I might like to portray it that way, he simply rediscovered the age-old practice that our next technology up society had quietly discarded. So this is Great Saginaw Lake. There's a lake up there. That's Northville down in the right corner. Edinburgh is really just a little village around the corner there. So this is the environment he grew up in. So this is the first building that he designed, Brownell Lumber. There it is under construction. This is still operating as a family lumber company. Oh, and let's see if I go back here. Down on the right-hand side there, Bruce built that small one-bedroom house as a testing house to have people come. Families would come and stay there over the weekend. He had all the outlets on separate little electric meters. Well, they're not little, they're like, look like a regular full-size meter. He would monitor their usage. The solar gain, that's one of the first houses with heat energy battery. So there's 3 feet of sand underneath that with a ductwork going through it. Store the solar gain from the south-facing windows. And that's our office now. So these are all, not all, but these are most of Bruce's houses that he's built, over 400, 17 states and Canada. Okay, so it was actually the Greek philosopher Socrates around 360 BC that described using the sun to warm Greek homes. Fellow philosopher Xenophon recorded this conversation in the memorabilia writings that he had done. Socrates advised that a well-designed house should face south. The sun would pour warmth into the room during winter, while a deep roof or portico would shield the interior from the harsh midday summer sun. It was a matter of fact, grounded in everyday experience of Athenian builders and homeowners. So you can see this is a sketch. So the house is the temple-like structure. You can see a ruin of one over there where they actually arched it to get more sun angle in during the winter months. And that's a contemporary house there where they're using more of the mass to heat the inside. A few hundred years later, the Romans engineered advanced use of thermal mass for heating. These are the baths of Caracalla with its hypocast powerhouse. There. Completed in 2016 CE, these baths covered over 100,000 square feet of heated floor, more than 2 football fields. The Romans built a crawl space of sorts, brick pillars, you see on the right there, the ruin, supporting a raised floor with hot air from a wood-fired furnace circulating in the space below with channels warming the thick masonry above, turning the floor into a radiant heat source. Archaeological reconstructions using modern measuring devices show the floors in the main bath 80 to 100 degrees during the winter months. The heat continued up into the walls, creating a gentle, even warmth throughout the massive stone chambers. And you can see they're rather huge there. The hypocaust transformed the building itself into a giant thermal battery, storing energy and releasing it slowly long after the fires died down. The Romans harnessed engineering mass and controlled airflow design, did not just heat a room, it heated 100,000 square feet at once with a single centralized system, which is sort of the precursor to our furnaces and ductwork stuff we're doing now. So fast forward 1956, Felix Traum took the ancient ideas and designed a wall using concrete or masonry facing south and placing just behind a layer of glass. Sunlight streams through the wall or through the glass and heats the wall. It then slowly transfers the warmth and releases it long after sunset, smoothing out temperature swings without a furnace. Field tests from the late 1950s and early 60s showed that a Traum wall supplied between 60 and 75% of a home's winter heating demand at typical temperate climate. All this without any moving parts or complex controls. The wall's mass acted like a battery, storing solar energy, then letting it trickle into living spaces as the air cooled outside. Which brings us to the mid-60s and Bruce Brownell's designs. Bruce combined ancient Greek practice of orienting to the southern sun and adding a thermal mass storage pioneered by the Romans and advanced in by Felix Traum, where he also added the vision to make use of emerging technologies in building insulation envelope sealing. This enabled him to reduce the overall heating demand. Now, the house only needed occasional supplemental heat on the harshest days, which could be accomplished with a fire and a wood stove for a few hours. And this heat also would be stored in the heat energy battery. So you probably are familiar with solar orientation. This is a diagram. Now, it says down here, it says from the 70s. The house, your site, so that one side faces due south. This side should have approximately 1/3 of its total area in glass. This, in essence, a solar collector. Currently, with Bruce's design and the amount of insulation and sealing we have in the houses, we're at 15%, not 33% of glass on the south. We don't need that much, and it just overheats in the summertime. Up on the right-hand side there is a criteria that Bruce developed. So if you go 30 degrees off of the sidewalls, east and west, and clear, and then arc 100 feet of all the trees on a level lot, that will reduce the any supplemental heating demand by another 25%. So if it's really cold out, -15, it's cloudy, and you have to start a fire or run other supplemental heat, could be electric, could be a heat pump, geothermal. So it's a low demand, but this would reduce that demand as well. And then there's a little section here. We do an envelope. Now, this isn't ours, but we do an envelope all the way around the living space, underneath the slab, walls, and we do the roofs. So we'll get to that next. But you can see where the winter sun comes down, comes through, heats the area. Summer sun, it's blocked by overhangs. and just a steep angle that is that. So here's a section of Bruce's, one of Bruce's houses. So you'll see all these arrows going around there. So what happens is you get the sun coming in from the south, windows, skylights, clear stories. That heats the inside up. Now that air rises. This central shaft here is a return air shaft. We have grills at the top. We also have grills down here near where your supplemental heat is. So it's a wood stove. And typically we louver those so that if you're not using the stove, we close it to maximize the pull from the highest point where all the heat is. So that comes down through the central shaft via a blower fan and gets pushed into the ducts that are in the concrete down here, or sand, depending on which method they use. The sand has a much longer duration. It can hold more BTUs than the concrete. But over the years, Bruce found it's cheaper to do the concrete, and typically we don't need that length of duration in the areas we build. So then that air goes through the concrete, it gets absorbed by concrete. Whatever's left comes up in the walls and out either near the floor, the exterior, or Bruce likes to put them on the windowsills so they actually bathe the windows with the warm air, so you don't have that cold feeling when you walk by a window. Now, he's very particular about windows. South-facing windows are only double pane and no reflective films. So we get maximum solar gain from those windows. Depending on the site, size of the house, you might also do those on the east and west side, and depending on foliage, and buildings, anything blocking that gain from happening. North side, if we do have windows, they'll be triple pane to maximize the resistance. So that's it. Basically, it goes 24/7. The fan runs 24/7. So the mass moderates the house. Typically, it stays between 68, 72 degrees year round. Now with solar, well, climate change, summer's getting hotter. We've been adding some heat pumps. We put a coil in the air shaft for the heat pump to cool it down. For the previous 40, 50 years, all you had to do was open the windows at night. It would cool the house down, cool the battery down, get up in the morning, close the windows, and it would stay cool because the battery's been cooled down. It's going to take the heat back out. But when it doesn't go below 78 or 80 degrees, that's as low as it's going to go. If that's what it says outside, that's what it's going to be inside. So I've done a handful already of additional adding of heat pumps. We did one geothermal. I think that was overkill, but. So this is a section detail of the heat energy battery. So this is an insulation going all the way around. The wall gets built right on top of there, so that duct is going up into the wall. This one is inside the wall, so that's going into the room. The wall is out here. This is the central main duct supply that runs, well, depending on design, the length of the house, and then all of these come off of that. And I can show you later, if we get to it, some construction photographs of it being built. So this is the detail at the roof. So all of his houses have cathedral ceilings because we want to maximize the volume, get as much energy as possible stored and transferred to the battery. So you see that we do 2 layers of rigid insulation, polyisocyanurate, and he even details this. So the decking, that's the decking. This guy is the rafter. Typically, he does like a 4x8 rafter, 2 feet or 4 feet on center, depending on what the roof system is. And we break that and let that inside run of insulation go up through that and connect to this level here. Then we add a little bit in that knee space here on the upper floor, and this one on the outside, then 2 layers up here with a nailing, 1-bys. So you don't have to nail the plywood all the way down to the decking. You nail these through 1 layer to the decking, and you nail this to the next layer. Over here is the installation method for the foam. Bruce only puts 2 nails in each layer, in each 4x8 sheet at the corners there. So the first layer goes on horizontal, 2 nails. That goes all up. The second layer goes up vertical. It all gets taped, and 2 nails there. And then this siding goes on that. So sometimes it'll be 1-by strapping. It goes horizontally, and we put board and batten, vertical board and batten on. Others have different detailing for different. So this is last year we entered the micro home competition. This is a little micro home section with our system in it. This is only 221 square feet, that building. But that shows you highlighted where the insulation is. And then this is the heat energy battery down here. So let's talk about performance. This is a house in Saratoga Springs, 1,600 square feet, 3 bedrooms, 2 baths. Less than 1/4 of the electricity is used for heat for this house. So these are over here 2010 costs. So heat and cooling was $329 for the year. If you use Syracuse's rates right now, 2026, that would be $430 for heating and cooling. So the average residential rate is $1,277, excluding heating, for electric. So the average cost of oil heat for that same house, same square footage, would be $2,935. So these people every year are saving $2,500 on heat and electric. So what is that? It's, say 15 years. $37,000 they've saved. So it's worth it for them to pay a little extra to do this design, do the extra insulation, all the sealing, all the details, because that money is going to come back to them. Now, this is even crazier. This is a 5,200 square foot house in Lake Placid. Shannon said, you guys know about degree days, heating degree days. It's the amount of heat to take per day to rate for the difference in temperature. So basically, if you wanted to be 70 degrees and it's 25 outside, that's 45 degrees of difference that you have to raise the temperature in the house to get it to where you want to do. So this house is 9,631 degree days. Albany is 5,954. I think Syracuse Yeah, I put it on here somewhere. 7,400. So it's over 2,000 more degree days at this house. This was monitored by an outside monitoring agency on municipal electric from April 2010, October 2009, 2010. So that's a 7-month heating period, October to April. Their cost for heating was $628. The next year for that cycle was $626. The average cost for oil heat for that same period is $10,766 today. $6,282 in 2010 dollars. So if you go back to 2010, they're saving $5,600 a year in heating costs with this house. The previous one was monitored by NYSERDA. I don't know who did the monitoring here. It may have been Brookhaven or one of the other So the other aspect of this is sustainability and contributions to the environment and the economy. Since 1975, collectively equal over 14,290 house years. So 48. So this was 10 years ago, over 10 years ago when this was calculated out. At 1,000 gallons of oil per year, that's 14 million gallons of oil not used by these homeowners. At $23,400 per home, that's $334 million to the local economy. At 80% and 4% sales tax, it equals $10 million to the local tax collector, because those people are spending that money locally. If it goes into oil, 10% of that stays, 90% of that goes outside of the community. 22,380 pounds of CO2 not emitted. That's 160,000 tons of CO2. This is why I am in awe of Bruce. One man has made this kind of effect on our environment and our economy in the Northeast. And then also another $2 million saved during the summer from peak, not having to use peak power to cool your house. And there's a bunch of breakdown in that sheet over there, but it's kind of boring. So let me see if I can pull this up here.
Bruce himself got some health issues, so he couldn't come to the class. David, this video interview, right?
Well, he's at a home builder show in Tupper Lake at the Wild Center, or at Build a Greener Adirondack Expo, and he's explaining this to a woman at the expo. I hope we have.
There's some houses we've done in the Adirondacks, as denoted by the green dots scattered around, or where I am, Great Sack, not the lake. We've done about 33 houses in the Adirondacks to date. across 40 years, these houses with an average cost for oil in 40 years of $1.25 per gallon across 40 years have saved a bunch of money. This sheet involves that. And I'm assuming that the average house burns about 800 gallons a year. Okay? My houses don't do that. Your house does do that. So you bought the 800 gallons of oil and across those 40 years, we saved by not buying 800 gallons of oil, these 33 houses, 590,000 gallons of oil. When you bought the oil, 10% of what you spent stayed here, 90% left here. And so this little sheet shows you that that was $1,000 or so, with about $100 staying here. My people who didn't buy the oil, they spent the money here. I went through the economy 6 times.
Yeah.
My contribution, my house's contribution is $4,600,000. The Adirondack. They collect the sales tax on that, $147,000. The county's collecting sales tax, $110,000. I didn't dump 11 tons downwind for the oil burn each year. I saved 6,800 tons of not going into the air. And this is more complicated explanation. We don't need humidifiers or dehumidifiers. There's not too much in the Adirondack. But because my houses don't need that, they didn't use 500 million kilowatt hours that my people didn't buy. So the grid had it, all of you. And that saved my people in the Adirondacks $75,000. Why aren't we doing more of this?
Exactly. I love the math.
Now I want to take it to this year, not 40 years, last year. Same 33 houses, saved 26,000 gallons of oil, contributed $554,000 to the Adirondacks, contributed $117,000 to New York State sales taxes last year, contributed $13,000 to the counties, didn't dump 307 tons of CO2 downwind, and saved 22,000 kilowatt hours, which my people didn't spend $3,300 on. How can we keep doing the other thing versus this thing? That's the message that I hope to get across.
Hey, Bruce, where can people find more information about these homes? Do you have a website?
Yeah, website would be, it's on handouts here, it's www.aaepassivesolar.com.
aaepassivesolar.com.
Correct.
Fantastic.
Yeah. I updated a little bit last year, but still a work in progress. So did you guys have any questions? You want to go back to anything, or you want to see some a house under construction, some of the detailing?
Any question for David before we get to the next?
I can't get too technical. That's Bruce's. But yeah, maybe the professor could help me out if you need. Okay, so this is I'm gonna say about 2,800 square foot house. So this is where we start. That's usually 8 to 12 inches of crushed stone with a drainage system on top of it. From there, we'll form up, put down a vapor barrier. This sheet is to keep stuff dry. Now we put down 2 layers of 2-inch rigid polyisocyanurate. So that's 4 inches total, which is roughly 28, 32 R rating. And you can see it's running up the sidewall there. See it going up there? Because that's going to continue right up the house. It's continuous. So now they're putting down the 2-inch slab that the ductwork's going to be mounted on. So this is 2-inch all the way around. You can see there's some drains in there already for the plumbing. So now the slab's down, and this right here is the return air shaft, roughly in the middle of the house as best we can do. This is the main duct going out here, and you can see all the takeoffs there that will run out to the exterior walls and then go up, whether go into this floor or go up to the upper floor. Here's a shot with all the ductwork in, all the risers going up. See them there, over here, with short ones that are going to be serving that first floor or lower level. Now, this plywood here is going to be the top of the slab. So form right to that. That way, if there's a problem, can always cut that out and get down in there. And if 60 years Bruce has been doing this, we've only had 2 houses that had a problem. One in Valatia near Albany that I dealt with last year. The third owners bought it. Second owner abandoned the ductwork, took it out, and wasn't using the battery. And the house was not very comfortable for the new owners and their 2 kids. So we reestablished that, and that ductwork was full of crap. Toys, mouse nests, all kinds of stuff. So now they're framing up. You can see here, they cut the holes already for the ducts in the base, in the bottom plate. In this instance, we're using 2x6 walls there. Now, even though we have that as a standard detail, most of his houses are post and beam. We're not going to insulate in those cavities because we're insulating outside of that. Our vapor barrier, moisture barrier is outside of all the wood. So here they're putting decking down. This is a 2-inch or maybe 1.5 inch flooring for the second floor. I think I have a better picture, but you can see right there, that wire for lighting, that is actually led into the top of that 4x10. Oh, there it is, yep. So they used to be able to just put the floor over top of that, but with more current codes, we're required to put a steel piece of sheet metal over top of that before the floor goes down. Protect that from a nail. Now in this house, we used attic trusses over the garage. Bruce is a huge proponent of having that bonus room up there. In fact, it ran plumbing, water lines, electric, everything to have another bathroom for an in-wall suite or a guest quarters with an exterior door. And you'll see that as we go through. There's overframing to give the overhang on the gable end there. So the trusses are there, and then it switches here. The gable truss is shorter than the attic trusses. So here's a shot So this is the connecting link here between the house and the garage. So this is all going to be completely sealed, 2 layers. You can see there's snow on the sheathing out there. But this is 2 layers here going all the way around that gable end, up these walls, across the top, back down again. All in the exterior of the building. There's Bruce explaining something adamantly, and the homeowner. So this is that section here in the detail where you'll see later on the insulation is going to come up here and go all the way up to meet the insulation on the other side of the sheathing, roof sheathing. Pretty steep roof. I wouldn't want to shingle it. So here you can see it here. That exterior insulation is going all the way up and clearing the rafters so that when the sheathing comes down here, the roof sheathing comes down, it stops on that side and picks up on the other side. It's kind of hard to see there, but you can see it. That's the insulation there coming up, and they've already put the roof deck on up to that point from the eave. And here it is inside. You see it going up there. Now, there'll be another layer on top of that on the inside, just to add, to make sure we don't have any, so we have a good thermal break there. So here's a shot of the corner. So the first layer goes in, butts into that layer, and the second layer overlaps that layer, and this second layer will overlap that layer, and these will all be taped corners. I think this is here for a deck, roof and a deck. You'll see that later on. They're working their way up the side there with the insulation. So this is a detail that Bruce does in all his houses. People say, oh, well, your floor is not going to get that solar gain because you got those sleepers on there in the wood floor. Well, we're not counting on the sun hitting that and warming it up. We're warming it up with the air through the ducts. And this allows us then on a slab-on grade situation to run wires through there, electrical wires, data wires, whatever we need to do in that space, because that's 1.5 inches deep there. So those areas, you can run a wire up through there to get to that wall. Or if for some reason you need a floor outlet somewhere. So here's where they're doing the detail I showed you before with the 1x lath on top of the first layer. So those sheets, 2 nails into the sheathing that's on the rafters, which is on this house, it's going to be probably a 2-inch tongue and groove. Then the lath goes through there all the way up, and those are covers for the skylights. They have to be packed out so you can frame to them. You have something nailed to the skylights around the holes in the insulation. And then the next layer will go on top and it'll just get nailed to those and not all the way through. So you don't have to have 4.5 inch, 5-inch nails to attach the insulation, even though you're only doing 2 per. So here's the sheathing going on with the second layer. You see the 2 layers there. So they put the insulation on and then the sheathing right on top of it as they work their way up. So they don't do all the insulations, they don't damage it, put any dents in it or break the foil. And they're almost up to the top there. And the windows are all taped off. I don't know if it's Sika tape or a different kind. But air sealing is a high priority around windows, doors, any penetrations. We do blower door tests once it's enclosed before any drywall goes on or finishes. So we can identify any areas of leakage. So this is the air shaft, and that's that main duct going through the concrete. And this is a splitter. So that's directly below the fan. So it diverts the air to both sides, both ends of the house, east and west, I think, in this instance. And that is put in just with 2 screws, so that after a while, you can adjust it and balance the system. Moving that like a ½ an inch will make a huge difference in the volume of air to either side of the house. There's looking from the top down, there's one of the grills that get the return air. I'm sorry, from the bottom up. So that's the top up there. So there's 2 grills up there at the highest point to pull the air from the peak, the hottest air. And then this one is here for the wood stove. So that would be louvered. So when the wood stove goes on, open it up, it sucks the hottest air right down, heats the battery up very quickly. So you don't have to stoke your stove for 8-hour burn or 10-hour burn. 4 hours, 5 hours, after dinner, you have a nice fire, let it go out. That will heat the battery enough to keep the house warm.
What material is the interior side of the shop?
This is a sound bat insulation board to reduce the noise from the fan and to keep it clean in there and seal it really well. And there's there should be some shots of the air shaft with the equipment in it as we get farther along. This is the interior again, showing the sleepers on the slab. It also makes it much easier to put the floor down because most homeowners want a wood floor. That's the king post there, and that's the air shaft. So we do ridge beams as opposed to ridge boards. Are you familiar with that difference? A ridge board is just keeping the rafters from pushing against each other. A ridge beam is actually holding them up. It's a structural member so that you can have the framed one side without the other side. So if you have a ridge board, you have to frame it going up so they oppose each other so it stays in place, or you get a crooked roof. So here's an example. The water lines are run through that space and up the wall. There's the ductwork going up. So coming out of the slab, and there's going up to the second floor. And it's hard to see there. There's the duct going to the windowsill. So I'm sure I have a picture of a window later on somewhere. So this is the chimney for the wood stove, and right there's the air shaft. That's going to get built out as well and finished. All right, I'll see you later pictures. Oh, so you can see it's like a rock wool there, the insulation inside the air shaft. There's the chimney right there. And there's the opening for this side. So this is a sound box, as Bruce calls it. So this is the bathroom. There's no exterior ventilation. We just allow the moisture and heat and smells from it to go up to the peak and get sucked down through the filters. Bruce specifies MERV 13 filters now for the house. There's 4 of them in a pattern, and he instructs the homeowner to start with 4 new ones and then every month replace 1. And so you need 12 for the year, I think. No, 15. But in order to keep from transfer of noise, he designed a little box that's lined with sound bats, sound insulation, and baffles, so that the air can transfer from here out into the next space without noise transferring, sounds, voices, bathroom noises. So here they're preparing for a deck. So that's a hardy plank type material, or a backer board, tile backer board, depending on the job, to protect the insulation from the deck and moisture underneath there, because we don't want to run the wood siding down behind there, as that's going to cause problems with dirt getting in there, moisture accumulating. This way, that's going to keep that from any rot happening there. So here's one. So this is the other side of the wall. So that inside, the opening's over here, and out here the opening's over here, and there's a baffle in there, and that's all lined with sound insulation. So it minimizes any transfer, any bouncing of the sound. But the air comes out, gets out, and goes up. And here's the vent in the windowsill. So that's going to warm that window up all day long. So when you walk by it, it won't feel that cold air like you would walking by these. No offense. There's the finished fireplace air shaft. Now they've got 2 grills there, and there's the outlet for the stove chimney, and the ash pit for the chimney as well. Just some interior shots. Shower. I haven't met that guy. Kitchen, looking from the loft. So this is an interesting thing that Bruce does. This is a roof deck. So this comes off the master bedroom. It's installed so that that lull can take it off. So this is built on the ground, and it's set on top of that roof after it's completed, the deck is. And then if you ever have to repair that roof, you just rent the lull, you come back in, you lift it off, put it on the ground, fix the roof, put it back again. Here's cleats. These cleats hold it in place. So that's the only thing that's attached to the roof. And those rubber sections down on the previous one have a pin, that bolt that runs up into the 4x4, so it can't move around. There they are underneath as well. So it's just, it goes in, just slides across that and drops down. There it is up there. And you can see where this is where that hardy board or tile backer was across here. Here's the air duct going up into that windowsill from the energy battery. Finish shot, living room, dining room. So one of the things that Bruce does is he puts interior windows in to borrow light. I don't think it's in this section here. Kitchen again. So this is a second floor, and there's a sleeping loft up here. There it is. So here's the air shafts. So these are the filters, 16 by 16, 2 inches thick, 4 of them. And they just slide in, drop down. Now this house has a coil for a heat pump right there. It also have a damper that closes when the heat pump turns on to force more air through the A coil, because it's not the whole size. The air shaft is 36 by 36. A coil's probably 24 by 24, like that, 18 by 28. So we put a damper in there that's open all the time until the coil comes on, and it shuts down, forces more air through the coil. More efficient. Again, there's the wood stove. There's the grill up there to capture that heat and get it going right down into the battery before it doesn't have to go all the way up to the ridge. Other side of the house. That's it. Let me see if I have that other shot. Here we go. So this is something that Bruce does. So this is a porch. So this is an alcove in the house where it's recessed in. And I believe that window is in the bathroom. This light is over the door downstairs. And he puts a skylight in here to provide light for that window in the bathroom. Oh, any questions? Any comments? Because everybody seems to be still awake. Yeah. Probably about 10 years ago, Bruce did some cost comparisons. So at that time, a code compliant house versus his house, it was about 15% more expensive for his house. But it's not apples to apples. If you want to go apples to apples, prices against the passive house. If you're at the passive house, so they're doing this stuff with high-tech things. I did it on that zero energy modular project where we had ERVs. The house was so tight. We required to have an energy recovery ventilation, which pulls outside air in, goes through an exchanger. So it pulls the heat or cool out of the air that's in the house. So you're recovering that heat and then putting it in, fresh air in with that heat or coldness. So you're not, don't have to heat it up in the winter time. You don't have to cool it down in summertime. That ERV does that for you. And then all we had was a heat pump for it. However, that house, I had specified this German built small wood stoves that also generates electricity. So you could charge your phone, watch a movie on your computer, just with a fire. But when the engineers did the calculations, after like 30 minutes, you have to put the fire out because the house would get too hot. It was so tight that, and we're recovering all of energy, you couldn't have a fire ever. But those houses, so it was 1,100 square feet. It cost $265,000 without the solar panels and batteries. So what's that, about $230 a square foot? That's probably more square foot than one of Bruce's houses, because you don't have the mechanical systems.
So I think that's a good question, but I agree that when you refer to compare to technology, you have to consider performance, right? What level of performance? That's another factor. So if you would probably like to have a fair comparison, you have to compare this technology with the passive pipes, which is considered more high performance, more airtime, lower energy building. Those type of apps would be more apple to apple comparison.
Yeah, and it really depends on what kind of house you're looking for. This is a custom designed house that we just looked at. The modulars were all the same, other than left hand and right hand for the site and the solar. Minimize the runs for electric and water and sewer and stuff. So all those utility stuff was on the driveway end of the house. So one was left hand, one was right hand. They're all the same, all factory built, trucked out on two trailers and put on a crawl space with no rat slab or anything, just earth. So it was a very efficient, cost-effective way to do that. And because we did 6 of them at a time, we got a very good price from the factory. They did the same thing, 3 of them, swap it over, 3 more, ship it out. So there's that as well. And that's vinyl siding. This is wood siding, much better finishes in here. They had laminate countertops.
But also another metric to be paid at, right, for traditional stuff, because you showed 2 examples of how much you save in terms of operational energy.
Yes.
During the life.
Yeah. So if you're looking at a 30-year mortgage, and you're saving, I don't know, say you're saving $1,500 a year, 30 years, that's $40,000 that you can spend for upgrades, and you're going to get that money back. And probably, depending on the house, even more than that. Like the house in Lake Placid was like $10,000 a year from heating oil to the passive solar. Yes, thank you.
Any other questions?
Okay, there's going to be a quiz. I'm sending it. I'm just joking.
Let's kind of take the game.
Thank you. My pleasure.
See you next Tuesday.
I'm coming back next Tuesday?